Twisted WSe2, the coolest superconductor you've never heard of. What do you get when you twist 2 layers of tungsten diselenide, WSe2, at a 5.0 degrees angle and apply a little electric field? A superconductor that could make your freezer look like a sauna. In a groundbreaking study published in Nature on January 22, 2025, a team of researchers led by Injie Guo from Columbia University has discovered superconductivity in twisted bilayer WSe2, a material that's giving graphene a run for its money. This discovery not only pushes the boundaries of superconductivity research but also opens up a whole new playground for exploring exotic quantum phenomena. Superconductors are materials that can conduct electricity without any resistance, but they usually require extremely cold temperatures to work. The holy grail of superconductivity research is finding materials that can achieve this feat at warmer temperatures, ideally closer to room temperature. Enter twisted bilayer WSe2. By stacking 2 layers of WSe2 and rotating them at a precise 5.0 degrees angle, the researchers created a moire superlattice, a pattern that emerges when 2 periodic structures overlap. This moire pattern gives rise to flat electronic bands, which are like highways for electrons to zip around without bumping into each other. The result? Superconductivity at a balmy 426 millikelvin mK, or about minus 272.7 degrees Celsius. Sure, that's still colder than Pluto, but it's a big deal because it shows that superconductivity isn't just a graphene thing, it can happen in other materials too. What makes this discovery even more exciting is the interplay between superconductivity and magnetism. The researchers found that the superconducting state emerges right next to a metallic state with antiferromagnetic (AFM) order. Think of it like a dance floor where superconductivity and magnetism are doing the tango. Sometimes they're in sync, and other times they're stepping on each other's toes. The superconductivity appears to be mediated by spin fluctuations, which are tiny magnetic ripples that help electrons pair up and glide through the material without resistance. This is similar to what happens in heavy fermion systems, a class of materials known for their exotic quantum behavior. The team used a clever device structure with multiple gates to control the electric field and carrier density, allowing them to fine-tune the conditions for superconductivity. They observed a sharp boundary between the superconducting and magnetic phases, suggesting that the 2 states are closely linked. This finding could help scientists better understand how superconductivity and magnetism coexist in other materials, potentially paving the way for new types of quantum devices. Of course, no scientific discovery comes without its challenges. One major limitation is the extremely low temperature required for superconductivity in twisted WSe2. While 426 mK is impressive, it's still a far cry from the room temperature superconductors that researchers dream of. Another hurdle is the complexity of the material itself. Creating twisted bilayer WSe2 with the perfect 5.0 degrees angle is no easy task, and even small deviations can throw off the delicate balance needed for superconductivity. But where there are challenges, there are also opportunities. The discovery of superconductivity in twisted WSe2 opens up new avenues for exploring correlated electron systems in 2-dimensional materials. Unlike graphene, WSe2 has a native band gap, strong spin-orbit coupling, and spin-valley locking, which could lead to even more exotic quantum states. The researchers also speculate that superconductivity in this system might be unconventional, meaning it's not driven by the usual electron-phonon interactions but by something more exotic, like spin fluctuations. This could provide valuable insights into the mechanisms behind high-temperature superconductivity in other materials. So, what does this mean for the future? If scientists can figure out how to tweak the twist angle or apply different electric fields, they might be able to push the critical temperature of superconductivity even higher. This could lead to practical applications in quantum computing, where superconductors are used to create qubits, the building blocks of quantum information. It could also revolutionize energy transmission, making it possible to send electricity across vast distances without losing any energy to resistance. In the meantime, the discovery of superconductivity in twisted WSe2 is a reminder that sometimes, all it takes is a little twist to uncover something extraordinary. Who knows what other quantum surprises are waiting to be discovered in the world of two-dimensional materials? One thing's for sure, the future of superconductivity is looking cooler than ever.